Okay, welcome to the lecture of the material science. Welcome indeed. Today is the typhoon. Yesterday it was typhoon, right? So I'm very happy to see you here today. So as usual, let's recall what we have learned on Wednesday. On Wednesday we learned the covalent bond. I hope you remember. And the covalent bond, we need to know it's valence electrons in a valence shell. In the atom, they share the electron to each other. Okay, they share the electron to each other, and they also shift the electrons. Okay, they also shift the electrons. So, for example, this one share, but because of the AVEE, they share. This one shift to the electron go to the atoms where it has a higher AVEE. Okay, so and that's why we need to we learn how to draw the molecular structures using Lewis theory, right? Okay, and then also we learn shell hybridization. For example, like ch4, and ch4 carbon has 2s2, 2p2, right? And in order to have chemical bondings with hydrogens, you need to hybridize s orbital and p orbital and become sp3 orbitals. So this is called shell hybridization. And also we learn energy of the heteronuclear bonds. For example, this bond, I just told you, this bond not only involve sharing electrons, but also involve shifting the electrons. So the energy of this bond is can be represented like this. Okay, this term represents energy, electron sharing. This term represents electron shifting. Okay, because you see this is chi x minus chi y, which is chi is the electronegativity. Okay, and we also want to know a material or a structure which has a ionic character. So the ionic character represent like this. Okay, I want you to remember this equation, which is very easy already. Okay, this will be your midterm exam. Please bring your calculator. And we also learn what is dipole, what is polar bond, and what is polar molecules. And this is going to have, we are going to have a Kahoot. The title of Kahoot is polar molecular. Okay, so I'll just let you know. Right, and also on Friday, we also study the molecular orbitals and the energy levels. So there are, for example, there are two atoms, and they close to each other, and then in the end they make a bonds. And what's the shapes? What's the molecular orbitals of this structure? We follow LCAOMO, linear combination of atomic orbitals to molecular orbitals. Right, so this is LACOMO. And then not only we want to know the molecular orbital, the shape of the molecular orbital, but also we want to know the molecular energy levels diagrams. So this is the atom energy diagrams. For example, this is an example of hydrogen, right? This is the energy diagrams. So if you have a molecular, hydrogen molecules, so the energy diagram will follow the conservation of energy state, right? You have one, and in the end you need to have two. Here, this is called conservation of energy state. So we have bonding molecular orbital and anti-bonding molecular orbitals. And this is the shape. According to LCAOMO, this is the shape of this orbital. This is the shape of this orbital. And not only to do the conservation of energy state, like one energy state becomes two energy states, but also we need to know how to put the electrons into these molecular orbitals. into these molecular energy states. And again, we follow alpha principle. There are 4 rules, right? I hope you still remember there are 4 rules. Right. And then on Friday, we also learn. Now, we also so there are because we can divide the molecular orbitals and the molecular energy level diagrams into 4 parts. The first part we learn is SS mixing in molecular orbitals, which is I just show you. For example, like hydrogen, helium molecules, lithium molecules, and barium molecules. So they follow S and S, right? S and S mixing in molecular orbital. So this is the shape. This is energy level diagram. Okay, and then S and P mixing is the heteronuclear or diatomic molecules like hydrofluoride, hydrochloride. So this is one, right? This is energy level diagram, looks like this. So like chlorine, you have 3P here and you have 1S here. So by the combination, you got an energy level diagram looks like this. Okay, and after that, we learn this is PP mixing in molecular orbitals. The PP mixing molecular orbitals, for example, like boron molecular, nitrogen molecular, oxygen molecular, and the fluorine molecular. Right, this is PP here, and then again they smear like they come to each other, they go to each other. Remember, I give you the example, and this is the shapes of this orbital, right? Bonding molecular orbital, anti-bonding molecular orbitals. So you have the shapes for each level. Okay, this is what we learn. And today we are going to continue this PP mixing in molecular orbitals, and then we will move to SPX to S mixing molecular orbitals. Okay, that's what we are going to learn today. So so this is one, right? This is one. Single bond and triple bond. Right. So the energy diagram of the PP mixing, it will involve like boron, carbon, nitrogen, oxygen, and fluorine. Right? So you have PZ, PX, PY here. So you have smear them together. So you will get an energy level. Principally, you will get an energy level diagram looks like this. This is pi. This is sigma bond, and these two are pi bond, and again pi bond, sigma bond. Okay, like boron molecules like this. So as I just show you, if you do the LC AOMO, you will get the orbital. The shape of orbital looks like this. Okay. However, it doesn't look the boron principally it needs to be looks like this. But however, there's an interaction between 2s and the 2p Z interaction. And 2s and 2p Z interaction, because the energy diagram looks slightly different. Well, I shouldn't say slightly. Huge different. Why? Here's the reason. The energy of the sigma 2p, sigma 2p here, sigma 2p orbitals is changed by ps mixing. The energy of the pi 2p and the sigma 2p are reversed. What's going on? This one and this one is reversed because of interaction of this one and this one. So it looks like this. Actually, this is the real energy level diagram. It's not like this. You might say, well, Professor, principally yes, but because of S and P interaction, this will reversed. So pi bond will go down and sigma bond will goes up. And also this anti-bonding molecule, this anti-bonding bond will be pulled down a little bit down here. So it's not equal. So So this energy level diagram here, energy level degree is not equal. Okay. Also the PS mixing change the energy of the sigma 2s and the sigma 2s anti-sigma 2s bond, such that they are no longer equal space. Okay, relatively to the energy of the free 2s orbital. So bond looks like this. Okay, so you have two pi bonds here. So this is the 2s and 2p interactions. So this is 2pz, this is 2s sigma 2s interaction. So you will see that this bar, this energy level needs to be reversed. However, for lithium, barium, boron, carbon, and nitrogen, it was pushed up. And go to oxygen, it will be dropped because of the energy, because of the electrons. So this energy level will be dropped like this. And this energy level will drop because of the electrons. Okay, I don't need you to remember these diagrams, but once you think of it, once you have chance to study this, you come back here and read it. Okay, so this is called 2s and 2pz interaction. So oxygen and fluorine is normal, but this one, from lithium to nitrogen, the energy level is of the 2s, 2pz and 2pxy will be reversed. So these are the reason I just told you. So please read this by yourself. And the most interesting is that because of this, there is a kind of phenomena called paramagnetic molecules. So what is paramagnetic molecules? I'm going to show you very soon. Right, so now let's take a look again for the energy level diagram of the nitrogen. So nitrogen has 2p, 2s, 2p, right? And nitrogen is helium 2s2, 2p3. So nitrogen has 5 valence electrons. So this is nitrogen atom, right? So you have 1, 2, 3, 4, 5, right? You have 5 electrons. And again, another nitrogen, there are 5 valence electrons, 1, 2, 3, 4, 5. Okay, and then when they get together, you have energy level diagram looks like this. As you can see, this is reversed. And this will be pulled a little bit down, which is not equal energy level. Okay, so it looks like this. So and then followed by alpha principle, you need to put all these electrons into this molecular energy state. Okay, so you have how many? You have 10 electrons. So you need to put these 10 electrons into these energy states. So start from the lowest energy, right? Lowest energy level, 1, 2, 3, 4, 5, and then 6 will be here, right? You follow the power, you follow the Hans rule, right? And then after that, you put this one here. You follow by Pauli exclusion principle. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. So you have energy. You have energy level diagram looks like this. So now I want to ask. So now you understand. This nitrogen shares 3 electrons to each other. So there are total 3 pairs of the electrons. Okay. So and you know that according to the Schrödinger equation, you will realize this is the shapes of the molecular orbitals. Okay. So there are 6 bonding electrons. So the bond order. Could you please tell me bond order? BO stands for bond order. Bond order is 6 minus 0 and divided by 2, right? So what's the bond order? 3, right? 3. So triple bonds. And then these 3 bonds, the energy is 946 kilojoule per mole, which is much larger than the hydrogen, which is single bond, right? The energy of a triple bond will be higher than the energy of a single bond. It makes sense to you, right? It makes sense. Okay, so energy is higher. So this is triple bond. Right, so after nitrogen, let's take a look of the oxygen. So this is energy level diagram of the oxygen. So remember that this is because of 2p and 2pz and 2s interaction. This is energy level diagram looks like this, but however for oxygen and fluorine, this energy level become normal. Remember? This reversed. Okay? So there are, for the anti-molecular orbitals, it looks all the same. It is all the same. But for the molecular orbitals, it will be reversed. So this is nuclear charge because of nuclear charge. Okay, so let's start to fill the electrons in this energy level diagram. This is oxygen, which is the electron configuration, which is helium 2s2, 2p4. So there are 6 electrons, right? So you need to put 12 electrons into this energy level diagrams. Okay, so let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 12. So you have 2 electrons in the anti-molecular orbitals. Okay, and the interesting things in the science is this shows an unpaired electron, and which has a property of the power magnetism. The power magnetism is that it's not a very strong magnet. Okay, it's like no magnet and magnet, but between very strong magnet and very no magnet is between. It's like metal insulator and you have a semiconductor. So once you apply electrical field, these 2 electrons started to act as a magnetic property. Okay. So we are going to talk about this very soon. So there are 6. So you know you have 6 bonding electrons, right? And then you have 2 anti-bonding electrons. So what's the bond order? The bond order will be 6 minus 2 divided by 2. So this is a double bond. Okay, and the energy of the oxygen is 498, which is greater than single bond. So double bond is greater than single bond. That's for sure, right? Right. Another example is fluorine molecular. The electron configuration of fluorine is 2s2 to 2p5. So there are 7 electrons. So if you put the electrons like this, you will realize. So there are 2 pairs of the electrons in the anti-bonding molecular orbital. And the bond order will be, so 6 bonding electrons, right? 6 bonding electrons. And then 4 anti-bonding electrons. And then bond order will be 1. 6 minus 4 divided by 2, that will be 1. So the bond energy is about 160 kilojoule per mole, which is less than single bond. This single bond, which is the energy of single bond, is less than the double bond, right? Okay. So now let's take a look of the paramagnetism. So the paramagnetism is caused by the presence of at least 1 pair unpaired electrons orbitals. This is unpaired electron. This is the energy level diagram, right? And then this is oxygen energy level diagram. You have at least 1 unpaired electrons. Okay, in atoms, molecules, or ions. of the paramagnetic materials, which result in their particles having a dipole moment. Okay, this dipole moment is a magnetic dipole moment. It's not electrical dipole moment. Right. So once you apply a magnetic field to this material, so for example, the oxygen molecule looks like this. The dipole of this magnetic dipole is randomly distributed. But once you apply the magnetic field, you tend to align these dipoles in such a way that for small fields and higher temperatures, that the induced field is proportional to the applied fields. So the magnetization is in same direction as the applied fields. So this is randomly distributed in this environment for the oxygen. But once you apply the electrical magnetic field from this to this direction, all the oxygen will align like this way, follow the magnetic field. So you must say, well, Professor, I never see oxygen will align, because oxygen in gas form, right? And the temperature, this environment, the thermal energy, which is temperature, is higher than the magnetic energy. So the energy is too strong in this environment, room temperature. So you cannot see the align. Once you, however, we are going to do an experiment for you. Today you see. There's a video to show you. So paramagnetism is a type of magnetism that occurs in the substance with a positive magnetic susceptibility, and it results in this substance being weak attractive by strong magnet. So it's weakly attractive, right? So this is what we call paramagnetism, which is opposite compared to the diamagnetism, which is no magnet property at all. Okay, so the example of this paramagnetism can be aluminum, magnesium, platinum, oxygen. So here we are going to make an example for you to know that what is the property of paramagnetism. So please read this by yourself. So I don't know whether you have seen this experiment or not. This is liquid oxygen, and liquid oxygen, which is the temperature is very low. It's below minus 200 Celsius. So it's liquid. So you have high density of the oxygen molecules in the liquid, and then because the temperature is very low, so you can regardless of the thermal energy. So there is no disruption of the thermal energy. So once this oxygen molecule meet the magnetic field, this oxygen will align, and this liquid oxygen will stay here. It won't drop. If you don't apply magnetic field here, if you pour the liquid oxygen through this channel, the oxygen will drop. Oxygen liquid will drop. But once you apply magnetic field here, the liquid oxygen will stay here. That's the very good evidence or very good experiment to show you that oxygen has the property of the paramagnetism, which is a paramagnetic material. Okay, oxygen molecules are magnetic dipoles, but at normal temperature they remain aligned since their interaction is very weak. Why? Because this temperature disturbs the interaction of the magnetic field and oxygen. So you need to do the experiment with a very low temperature. So the paramagnetism is much weaker than ferromagnetism, which is the magnetism associated with the iron or materials like irons, whose magnetic dipoles interact strongly and align together at a room temperature. Remember, this is room temperature, right? To increase a very strong magnetic field. So I have a video for you to know what I'm talking about. Right. So now we understand if you have unpaired electrons in the antimolecular orbitals, you will have a property of a paramagnetism, right? Okay, so again, let's go back to the 2s2p interaction. This is energy level diagrams, which is the 2p energy level is here, and go down and reverse in oxygen. So for the magnetism, take a look, where is the unpaired? So this is unpaired, right? Paramagnetism, and this is diamagnetism, and this is diamagnetism, and then this one, paramagnetism, paramagnetic, okay, and this is what? Diamagnetic. So when you see the unpaired, you realize it's very likely is a paramagnetic material. So for the bond order, you know how to do the bond order, right? So this bond order is 1, why? Because this, okay, and 2, right? 3, I just show you, right? 2, right? And then 1. Okay, this is bond order. And then for the observation bond associated energies, what does that mean? The energy of the bonding, right? Energy of bonding. So this one, if this one is 290 kilojoule per mole, okay, if a single bond is 290, how about double bond? Will it be stronger or weaker? The double bond, stronger, right? So it's 620. You don't need to remember this number, but you need to remember double bond is stronger than single bond. And if you have a triple bond, that's 942. And this is single bond, double bond, and then single bond. So energy increase from single bond to triple bond, and decrease from triple bond to single bond. Right. How about length? The bond length. Bond length means what? Two atoms, how far away from each other, right? So this one is, if this is 159 picometer, double bond will be shorter, right? Will be shorter. That means it's closer, which makes it stronger, right? The energy, and then much closer, and then increase and increase. Okay. Right. So this is what we just talked about, the sigma bond and pi bond. You know, sigma bond always tell you that the electron cloud or electron density between two nucleus is continuous. That's why we call this a sigma bond. And this involves SS mixing, SP mixing, PP mixing. PP mixing especially in the XL. Okay, and then for the pi bond is PP lateral male. And then the definition of the pi bond is what? Between two nucleus, the electron density is not continuous. Okay, this is the definition of a pi bond. So if you have sigma bond and pi bond, you can have single bond, triple bond, and double bond, triple bond. This is the example: single bond for fluorine, double bond for oxygen, and triple bond for the nitrogen. Okay, and also we learn 2s2p interaction, and we learn the oxygen paramagnetism, right? So this is a periodical table regarding the magnetism at room temperature. Okay, you can have different properties at very high temperature or very low temperature. Right, okay, so next topic will be the multi-bonds, which is hybridized orbitals. I hope you still remember what is hybridized orbital. But let me see that. I think before that, let's play Kahoot. This topic I'm going to talk is, again, multiple bonds, but this type of multiple bond is hybridized. Okay, hybridized. Do you remember hybridization? So we already studied sp3 hybridization, But how about sp2? Have you heard about sp2 hybridization? So this is a double bond. Okay, so it's mixing the s orbital and p orbital. But S and P will be hybridized. So the box notation of carbon, remember this? The box notation. So this is 2s, 2px, 2px, 2py, 2pz, and 1, 2, 3, 4, 5, 6. So there are 4 electrons here. And this is valence shell. And once you need to have 4 hydrogens, so there are only 2 pairs to fill. And we already learned, if in the case of the methane, you need to have sp3 hybridization, which is you need to put these 4 boxes into the same level, right? 4 boxes together and to make it in the same energy level, right? So you have 4 individual and the same energy electrons, and so that you can have another 4 hydrogen atoms to put it together, to put it into the same level, right? So as a result, you got methane like this. That's the exam. That's the exam of the question of the Kahoot, right? Okay, so you have sigma bond. You have 4 sigma bonds. However, in the case of this C2H4, which is ethylene, and what happened? What are we going to rearrange this hybridization? That will be, I also have 4 hydrogens. So I divided this into 3 and 1. So this will be called for sigma bond. This is for pi bond. So this sp2 and this is p here. So you have what? You have 1, 2, 3, 4. Like this. Again, the same as the sp3, but you separate this energy level into 2. Okay, so what's going on? So 2s, 2px, 2py, and 2pz. And then you have this double bond here with the 4 hydrogen. So this is what we call sp2 hybridization. Okay? And you have sigma bond, and pi bond. So sigma bond, and pi bond. Okay? So I hope you still remember, according to the Schrödinger equation, this is the shape of the sp3 hybridization. It was like this, 2s, 2p, and hybridization looks like it becomes a sp3 hybrid orbitals. It looks like this, but if you have 4, it becomes a tetrahedral sp3 hybrid orbitals. So this one hiding inside, right? So you have 1, 2, 3, 4 here. How about and then how about sp2? sp2 is 2s, 2px, 2py, and hybrids look like this. So you have it's sp2 hybrid orbitals. So you have 3. It looks like this in the same plane. However, you have 1 extra p here. So this is sp2, and the p orbitals here. Okay, this is sp hybrid orbitals. Right. So this is double bond, and I just show you, right? Just we know that. Okay. So you have 1 connect to here, 1 connect to here, and then here they are double bond. So this is the shape of the sigma bond, and this is the shape of the pi bond. Right, if you smear this together. Right, okay. So the molecular shape of the ethylene will be like this. So it's in the same plate. So this is double bond and single bond, and you can see this is we call stick model of the molecular, and this is sphere model of the molecular. Okay, and if you put all the orbitals together, it looks like this. Right, and how about ethylene? Ethylene has a triple bond. So this is sp hybridization. It's not sp2, sp3, it's sp. Okay, so this is the summary for you to read. Please go to read this by yourself. Right, and then next topic will be the shape of the molecule, but unfortunately this is almost chemistry, and then we don't have much time this semester, so I will skip this topic. So I just want to show you that you know, it's very interesting. And here I just want to show you that because you know, when you have single bond for methane, triple bond for ethylene, and then triple bond for ethylene, this is different. Ethylene is very, because you have triple bond, so energies, if you release this energy, then this has a very high energy. So you know, when you do the cutting or welding, you always use ethylene as a field, and you process with oxygen with like a very, so it's like combustion. So if you have a combustion reaction, you will produce a lot of energy, and to make the temperature very high. If you make the temperature very high, everything will be melt, right? Like 3,500 Celsius. So that's why this triple bond has a tremendous energy once you do the combustion reaction. Okay. And also, if you have rules to do the molecular, to make the molecular shapes, then we follow VSEPR. But again, unfortunately, I don't have time to talk about this. So if you are interested in this topic, please read this by yourself. Okay. So they are very interesting topics. And here I just want to talk about the carbon. You know, as we know, that carbon is one of very important elements in our world. And you know, just now, methane, ethylene, and ethylene, they are all very nice, very good chemicals to have very different applications. Another chemicals for the carbon is diamond and graphite. So the diamond, we know is sp3, right? sp3 hybridization, because one carbon will have another 4 carbons surrounding, and then this is called sp3 hybridization. So it's a 3-dimensional covalent atomic arrays. So this is what we call diamond crystal structure. So if you replace this carbon to silicon, that will become silicon crystal, right? Silicon crystal. And it's very strong, so it's very hard. And it's a high index of reflection because it is a crystal. So it's transparent. Diamond is very beautiful, right? All the light go into this diamond will reflect back. That's why if this is in a very dark place, and if this is a very dark place, there's no light, and you have a diamond, and you will be the most shining lady or most shining person in this environment, right? Because every eye can see you. Nobody can see if you don't have a diamond. So this is a very precious metal. Very precious material. That's why ladies like it. Right? Ladies like it very much. And also this represents forever because it's very stable. So if you have a diamond, you can dash it forever. It's not like iron. You know, iron will rust, will become iron oxide. But this diamond is very represents shining and forever. So that's why it's very expensive and ladies like it. Well, some men like it because it's expensive, right? Okay. But for graphite, it's dark, it's black. So it's all made of carbon. This is sp3, this is sp2. So it's all made of the same element, but only different structure. And it makes things very different. For example, this diamond is very shining, right? It's transparent, but the graphite is dark. Okay, And because of sp2 hybridization, and you have a p orbitals, you have a free p orbitals here. And p orbital has a delocalized element, delocalized electrons. So delocalized electrons results in electron conductivity. So you have free p orbitals in the different angle, in a different direction. So this is graphite and this is p orbitals. So electron can travel through these planes because of the free delocalized electron. Okay, that's why it makes graphite as a very high conductivity. But compared to diamond, there's no free electrons, so diamond is a very good insulator. But graphite is a very good has a very good electrical conductivity. Okay, which is different. And then diamond is transparent, but graphite is black. Okay, and graphite is a very stable. Also, is a very stable carbon at room temperature. So actually, the graphite is more stable than diamond. Okay, in a room temperature. So when you study this, you study this course, and in the future, if you want to give, if your girlfriend asks you for a diamond, you say no, diamond is not stable. Graphite is more stable, so you can buy graphite to her, and then you say, for us a marriage, engaged present, right? You say, my professor told me that graphite is more stable than diamond, so we don't need we don't need diamond, we just need graphite. Okay, so that's good, right? So you save a lot of money for the marriage. Of course, your girlfriend will say goodbye to you because you give him graphite, not instead of diamond. Okay, just a joke. That's a joke. Nobody understand? Okay, good. Right. Okay. Anyway, so graphite is very stable, especially in the room temperature. Okay. So let's summarize the property of the covalent bonds. The covalent bonds has saturated 2 atoms only, and they share the electrons pair. Again, the covalent bond is directional. You know, this bond has a dipole, right? So the bond has a directional, strong, weak, strong, weak. So this is directional. So if I ask you, is ionic bond directional or non-directional? Which one? If I give you a question and ask you, ionic bond, is ionic bond directional or non-directional? Which one? Non-directional, right? Because as a crystal structures, the ionic bond will bond on the left, on the right, on the top, on the bottom, in the front, in the back. So it's all around, 3-dimensional bondings. So it's non-directional. But for the covalent bond, it's directional. Okay? So because of dipole. And then sp3 is tetrahedral molecular structures, and sp2 is planar structure, right? And for electron structures indicates molecular bondings and molecular shapes. So it really depends on the electron structures. You will affect the molecular bondings, and molecular bonding will affect the molecular structure, molecular shapes. And the property of covalent bond, it can be very strong like a diamond. It can be very weak like a bismuth. Okay, the melting point is very low compared to this melting point. And it can be electrically, it can be thermal insulative. So it there depends on the bonding properties. Okay. So for the covalent bond, I hope you learn dipole, polar bond, and polar moleculars through the Kahoot today and the lecture on Wednesday. And then bonding covalent bonds, you have ionic character and you have bond order. Please remember this. And for the molecular orbitals, you follow LCAOMO, and you also need to know the shear hybridization. For the molecular energy level diagram, you need to know the conservation of energy states. and alpha principle. For the molecular skeleton, you follow Lewis structure. We skip this topic, right? For the molecular shapes, we follow the VSEPR, okay, which is electron. You need to know the electron domain. Right. So next topic will be magnetic bonding, because I think I don't have time to talk about this topic. So I think I want to stop here. Okay.